Hello everybody. We're going to start section 14.8 on something called Lagrange multipliers, which is going to help us optimize functions to find either the absolute max or absolute min. I do want to transition from 14.7 to this section though, because it's very intertwined. And remember from 14.7, when we were looking for extreme values, we had a continuous function f of two variables, but we were considering that function being on a closed bounded region D. So for example, here is a closed bounded region, and so we were restricting the domain of this function on this set D. Here I just drew a possible surface for this function, and we realized that we weren't looking at the entire surface, but we were only looking at the part of the surface corresponding to your closed bounded region D. And so then that would be this green part of the surface only. And so you would ignore everything else. And so then the extreme value theorem for functions of two variables told us that we should be able to find an absolute max and min for points that lied on this set D. And so through this example here, just to kind of give you an idea, we see that if we ignored everything but the green part of our surface, we reach the absolute minimum at this point that lies on the boundary of D, versus the absolute maximum corresponds to a point inside our region D, right? And so I was just writing this comment here that says sometimes we found either the absolute max or absolute min on the boundary of D. And that's, like in this picture that I drew here, that's an example of us finding the absolute minimum of this function on the boundary. Sometimes all the points might be inside of it that give you the absolute max or min, or maybe they just lie on the boundary. But for these problems, we saw how complicated it could be when we were trying to look for critical points that lied only on the boundary. And so 14.7 talks about this a little bit more, but in a different way, okay? So for section 14.8, we are still going to consider a continuous function f of two variables, but now it's going to be subject to a curve on the xy plane. And what I mean by subject to is that we're only going to be looking at points that lie on that curve. Okay, so we're not thinking of it as a region, a 2D region that we're restricting ourselves to. We're just restricting ourselves to a possible curve. So unlike the scenario here, we're not going to consider the inside region of D here. We're only going to care about the boundary of it. Okay, and that boundary may be some kind of closed path like this one, some circular-ish path, or it could just be a straight line. So it's just curves this time, okay? And so for example, on this curve, we only are going to be plugging in points that lie on that curve. And so if we use the same function that I did in the previous example, and we have this as a surface, if we restrict ourselves just to the points on the curve, then we're only going to be looking at this green curve on the surface, and we're going to ignore everything else. And so then on this green curve, notice that we're going to be able to find an absolute maximum corresponding to this point on my curve down here, and an absolute minimum corresponding to this point that lies on the curve over here, okay? And so we're going to be able to find these extreme values now subject to points that lie on a curve versus a region this time. And I just wrote a note here that it turns out that this curve is going to end up being a level curve that we're going to be considering, okay? So that's the difference between what we did before versus what we're doing now, is that we're just looking at extreme values that lie on curves versus an entire region inside of it, okay? And the method we're going to use is very different from what we did in the previous section. And some of the similarities is that we still kind of have to solve systems of equations using partials, so that will still apply. but how we get to those systems of equations the theory is a little bit different, okay? So let's see how we're going to do this. So recall from calculus, and I think even pre-calculus, there's a popular optimization problem that's usually presented to students when you're covering optimization stuff. It's a rectangular fence problem. So let's say here you're building a rectangular fence and only have 10 feet of fencing, okay? Which dimensions will give you the maximal area? So you can make a rectangle that's very skinny, or skinny vertically, or it could be very boxy, but you're only allowed to have 10 feet of fencing. So in terms of this geometric object, that will correspond to the perimeter. And the question is asking us which dimensions. So if it's let's say we make x be this dimension and y this dimension, we want to find the dimensions x and y that will make the area of this rectangle maximal, okay? And so we rewrite this using our formulas that you learn in geometry to find the area of a rectangle that's base times height. So that's x times y, that's where this comes. And the perimeter is the sum of these two lengths, which is 2x, plus these two lengths, which is 2y, okay? And from here, you were able to do this in calculus by saying, hey, you know what, the perimeter I'm told is 10 feet for this fencing here, and I have to use all 10 feet. So this perimeter is going to be equal to 10. And so in Calc 1, what you learned was, well, let me isolate one of the variables, plug that expression that I get into this formula for my area, and then turn this function into a function of one variable, either all in terms of x's or all in terms of y's, and then you use derivatives and you did all that theory you learned in Calc 1, okay, to help you find those dimensions. But what we're going to do is we're going to do this a little differently, because now if we notice, we have that the area is written in terms of x and y, and so we can think of your area as a function of x and y. And so when they're asking us to find the maximal area, what they're asking us is, if I consider this function in terms of x and y, I want to find the absolute max of my value of a. But because I need to satisfy this condition, this is called the constraint of this optimization problem, that this equation must be satisfied. Whatever x and y values I use to calculate my area, they're subject to satisfying this perimeter relationship, okay? But what we're going to do is we're going to let this side of my constraint, we're going to define a new function called g, which is usually called a constraint function. We're going to define it to be the expression that usually has all the variables that you're using. And if I do that, and I define this new function g, this equation just means I'm setting the function g equal to 10. Okay? And why would you do that? Well, by creating this new equation, 2x plus 2y, and setting it equal to 10, what this is now being considered is, you're now going to consider this equation the level curve of your function g, who will always output 10. Okay? So I'm going to say that again. This equation, by defining g this way, this equation now has a new meaning. It's now considered to be the level curve of g, such that any 2 points you plug in here will have to output 10. Okay? Which is exactly what we've kind of been saying earlier, that any x and y values that you use need to satisfy the perimeter equaling 10. And so this is kind of saying the same thing, but in a different way now with functions of two variables. Okay? So what we're trying to do is we need to find an absolute max for my function. I put f here, it should be a. For my function a, for points subject to the level curve of our constraint function g, such that they satisfy this equation, okay? And if we graph this equation and we think of it as a level curve of the function g, the graph of it is going to live on the xy plane, right? So here's my level curve for, equation, which is just 2x plus 2y equals 10. I simplify it by dividing by 2, and I rewrite it in slope-intercept form. And notice that we got this line right here, okay? And so what this line is doing is that it's containing all the x and y values that satisfy my constraint, which means that it has two meanings. One, it's in terms of the rectangle, it contains all the x and y dimensions whose perimeters will always equal 10, okay? But in terms of a level curve, it also contains all the points x comma y that when you plug them into G will output 10. So they're kind of saying the same thing but in different ways, okay? And so what we're doing is we're going to be plugging in all the x, y points that lie on this line, and those are the ones you're plugging into your function. And then for all those points you're plugging in, you want to figure out which one will give you the absolute max area. Okay, so that's what we're trying to do. We're only plugging in points that lie on this line, and we want to figure out which one will give us an absolute max. So if we look at this in GeoGebra, let's let it load for a little bit. Hopefully it doesn't take too long. Let me move this over here. Okay, so hold on. Let's make sure it loads. Are you there? Okay. So let me write it here. There we go. Okay. So I'm going to graph the level curve. Here it is. It's right here in the on the xy plane, and it's also here on the xy plane. It's the same level curve, but it's just given you're viewing it in R2. Here you're viewing it in R3. Okay. So it's the same level curve. Okay. We're trying to optimize the function a equal to x times y, which I rewrote it as a function right here. And so that's this function with this surface. Okay? This is the surface of this function, x times y. And because we're only looking at points that lie on this level curve here, that will correspond to points that lie on the surface above, well, not so much above, but for points that lie on that level curve, that black level curve, 2x plus 2y equals 10. And so when I plug in those points into my function, I'm getting all the points that lie on the surface, which looks like this parabolic curve here. And so what I want to do is I want to find which points that lie on my level curve will give me an absolute max. And so we can see that it's going to happen somewhere here. So it should happen somewhere in the middle of my constraint function. So for some points that lie somewhere here, it looks like I'm going to get an absolute max. Okay. Now, what I want us to do is I want us to consider. Now we're going to consider the level curves of my function a, which equals x times y. Okay. And so I'm going to let, right now a is acting like the z variable, the output, okay? Let's look at what happens if we let z equal different values. And I'm going to move this around. And so right now, just imagine this variable c is equaling different areas. So I'm letting my output of my function equal different constants, right, to get the level curves of that function. So right now c is those constants I'm letting a equal, okay? So for different areas, right, this is corresponding to this. Let me see if I can, let me get rid of this, and let me get rid of this. Okay, actually not this one. So if you guys look right here, look at how this plane intersects the surface. all these points on my surface all have the same output value, which means they all are corresponding to points that will have the same area, okay? All points that correspond to the same area, but because we are restricting ourselves to only use points that lie on my constraint function here given by this line, which is over here in R3, I'm only going to be looking at points that lie on this blue curve, but notice that where it intersects this guy here, this kind of parabolic intersection here, this point here and this point here on the level curve is telling me that I have equal area for a rectangular with dimension whatever x and y point it has here, and whatever x and y value I have for this point over here, I have the same area of my rectangle. Okay. So now let's draw the level curves of my area function. Let's put that in R2. So that's right here. So the black curve is the constraint. These are the points that we're allowed to input. Versus the green curves are the level curves of my area function, which means any point I plug in from this green level curve will have the same area. In this case, let's say I want the area to equal 1. If I want the area to equal 1, oh, will it go? I guess 1.1. It's not going to let me choose 1. If I want the area to equal 1.5, I can choose any point on this green level curve, which corresponds to this piece here. And any point here will give me the same area, which means that if I pick this point where I intersect the constraint function with the green level curve, that gives me the same area, and this point down here gives me the same area right there. Okay. Okay. Let me let's go back to what we're doing though. So I want to find where points that lie on my constraint function that will have maximal area. So what we're going to do over here is I'm going to let the blue plane, which corresponds to output values of my area, right? That's my C. I'm letting my area equal these constants C. And we're going to move it up until we get to that tip, because that's where the area is maximal. So I'm going to move this up as it goes towards the tip. And it's going to keep going, it's going to keep going, it's going to keep going. And notice that over here, the level curve is getting close to the tip of it, right? And notice that when I get to the actual, let's see, if I go a little bit over, now my level curve doesn't touch my constraint curve, which means that there is no points that lie on this black curve that will give me the area corresponding to this green level curve. And so that's not what we want though. We want to find points on the constraint curve that will give me maximal area. So they have to touch. But notice that for that to happen, that's somewhere like right there. So notice that at the very tip of my blue curve, I have maximal area, and that corresponds to points that lie on my constraint curve. And notice that happens when the constraint curve is tangent to the level curve of my function I'm trying to optimize, of my area function. So when the area function's level curve is tangent to the constraint curve, I'm noticing that that's giving me the point, it's corresponding to the point where I have optimal maximal area. So if we can find the coordinates of this point where they intersect, that will help answer the question to give me the dimensions x and y that will give me the maximal area. So if I can find that point where they intersect, that will help me answer my question. Okay? Okay. So let me go back to what we were saying here. Oh no. Hold on. Let's wait. I spent too much time on this, on GeoGebra. Okay, so let me go back down. Okay. So remember, that was the goal. and we considered the level curves. We considered the level curves of my area function, and analyzed that at the max value, subject to the constraint curve, we saw that the level curve of A is tangent to the curve of my constraint function at the point where A is maximal. Okay? And let's look at a different example and put this one on hold for now, just to see if that happens again, and just to kind of analyze a different example and looking at their level curves, just to see what happens with that one. Okay? So let's consider a different function now. Let's say it's this function, x plus y plus 2, where your points x comma y have to satisfy this constraint function, this constraint equation now, which, if you look at it, is just the equation of the unit circle. And so we're going to copy the same thing. We're going to say, well, I'm going to let g equal x squared plus y squared. And so now this equation, I can think of it as the level curve of g equaling 1, which again is just the unit circle. Okay? And we want to find the absolute maximum of this function so that those points have to lie on this unit circle. Okay? Which means they have to lie on the level curve of g themselves. So let's do that. Let me go back to GeoGebra. Let me block these out for now while this thing loads. Let me close it. Give me a minute. And then let's open up the other one because I had that one prepped. Okay. So now, oh, whoa, what happened over here? So now, let me zoom in a little bit. Now we're going to have this level curve, which is the unit circle, x squared plus y squared equals 1. And then this is now the surface of the function, x plus y equals 2, which notice it's just z equals to x plus y plus 2, which is just a plane because it's a linear equation. And I want to look at only points that correspond to my constraint unit circle. And so then that will be this blue curve that lies exactly above my, my constraint curve. Okay, so I'm only plugging in points from my black level curve here. Let's see if I can zoom in. Perfect. And I want to find the absolute maximum for points that only lie on this level curve, which is this one right here. And so if we look at it, that should happen somewhere here, somewhere where x and y are both positive. So somewhere here is where it's going to give me a point that corresponds to the absolute maximum on my for the function where I'm restricting my points to only come from the level curve. Okay? And so now when I look at the level curves of my function f, okay, I'm going to do the same thing I did before. Start from the bottom. And then notice that when I look at different level curves of my function, now the level curves of my function f are just straight lines. And so then that's why they're going to look like this. Okay? And so as the values of z go up, right? That's where this this plane z equals that constant is intersecting the surface of my function, which is the red plane, and it's intersecting at this line right here. But I want to move my z values as high as I can so that I hit the maximal z value on my blue curve. So I'm going to move that, and I want it to be so that it's at that maximal value. If I go a little bit over, notice that I'm no longer on the blue curve, which is not what we want, because we're looking for the maximal values of z for points that lie on the black constraint curve. And so therefore those z values have to correspond to the z values of our blue curve here. So I need to move my level curve a little bit down. And so then notice that now if I get rid of the surface, whoops. Yeah. Notice that now I'm reaching the maximal value of my blue curve, and that happens when the level curve of my function is tangent again to the level curve of my constraint function. So it happened again, okay? And notice that that has to happen because if the level curve of your function doesn't intersect your level curve of your constraint function in a tangent way, then you should be able to raise the z value of the level curve of the function a little bit more. But if you do that, and it's supposed to be at the maximal z value, then you will no longer be intersecting the level curve of your constraint. And so, like if I did this, for example, if I moved it a little bit higher, I can't keep increasing it because I'm supposed to have reached the maximal z value corresponding to my constraint function. And so that's why it has to happen in a tangent way, okay? So both this example and showing us insight into this particular fact that happens in general, okay? So notice again that the point where f is maximal, the level curve of f and the level curve of your constraint are tangent, and this is true in general for any continuous function. So generally, for a continuous function f of two variables, if f has an absolute max or an absolute min, subject to a constraint given by some equation which corresponds to the level curve of your constraint function, and it happens to have an absolute max at a particular point, x naught, y naught, then in general it's true that the level curve of the function containing that point where you're reaching absolute maximum and the level curve of the constraint function are going to be tangent, okay? They're going to be tangent. So the level curve of your function corresponding to the maximal z value happening at a particular point, and the level curve of your constraint, they're always going to be tangent there, okay? Because otherwise, you're going to be able to raise the constant for z a little bit more, but that can't happen since you're assuming it's happening at the maximal z value, okay? And so that's why they have to intersect in a tangent way. Okay? And so what this implies is that the level curves have a common tangent line at that point. Since they're both intersecting in a tangent manner at this particular point, they're going to have a common tangent line at this point, okay? So we can conclude that. So they're going to intersect at the point that gives us absolute maximum or absolute minimum of our function. And so therefore, they have a common tangent line at that point. The level curves do. Okay. So now actually, I should write a little line right here. So now we're going to put that conclusion that we made on the side, and we're going to use it in a little bit. Now, since the gradient of the function at this point is orthogonal to the level curve containing that point, remember this was a fact we learned in our previous sections, that the gradient vector is orthogonal to the level curve containing that point. And the gradient for g at that point is also orthogonal to the level curve of the constraint function that we're considering. Okay, so these two gradients have to be orthogonal to the level curve containing this point. Well, since they're both orthogonal to the level curves, and the level curves both have a common tangent line at that point, then the gradients of f and the gradient of g at that exact point are both orthogonal to that common tangent line at that point. And since they're both orthogonal to that common tangent line, both of those gradient vectors must be parallel to one another. And since they're both parallel to one another, that tells us that there has to exist a scalar, which we're going to use now the Greek letter lambda. We're going to call that scalar lambda here. That's going to tell us that because these two gradient vectors are parallel, they're scalar multiples of one another, the vectors. Usually we wrote the constant to be k or c, but for this section, we're going to use lambda because it has a special name. This scalar is called the Lagrange multiplier. Okay, so it's special to these problems, these optimization problems, because wherever you're going to have, at whatever point you have absolute max or absolute min, the gradients at those points are scalar multiples of one another given by this scalar called the Lagrange multiplier. Okay, and so let's return to our ultimate goal. Remember, we're trying to find the absolute max and the absolute min. Let me go back up to the very top. We're trying to find the absolute max and absolute min of my function constrained to points that only lie on a level curve given by our constraint function. And so how do we find those points? So to find the absolute max and absolute min of your function subject to some constraint equation, and assuming that these extreme values exist, meaning that it does have an absolute max and then there is an absolute min, and we don't want the gradient of g to be the zero vector, otherwise this is not going to work here. What we're going to do is we're going to find all the points x comma y that will satisfy the gradients being scalar multiples of one another, and of course those points must satisfy the constraint. And so this is going to help you create a new system of equations, because this here tells you that f partial with respect to x has to be equal to a lambda multiple of g partial with respect to x. F partial with respect to y has to be equal to a lambda multiple of g partial with respect to y. And you're going to have to satisfy the equation given by the constraint. So this will create a system of equations that you're going to have to solve, okay? So this will create a system of equations. You're going to find a bunch of different points. And then whatever points you find, you're going to evaluate f at these points to determine which ones are giving you absolute maximum and which ones are giving you absolute minimum, because they have to do either or. Okay? So this is the process that we're going to take for this section to help us find the absolute maximum and absolute minimum. Check out the other videos to see how we do that. All right, take care.